Okay, this is David Zierler, Director of the Caltech Heritage Program. It is Thursday, November 18th, 2021. It is my great pleasure to be here with Professor Barry Simon. Barry, it's wonderful to be with you. Thank you for joining me.
My pleasure.
Barry, to start, would you tell me, please, your title and institutional affiliation?
I am the IBM Professor of Theoretical Physics and Mathematics. Mathematics and Theoretical Physics, emeritus at the California Institute of Technology.
Barry, we'll unpack the title right from the beginning. Now, Professor of Mathematics and Theoretical Physics, is that a joint appointment between two departments?
Yes and no. So you have to remember that Caltech officially doesn't, quote, have departments. It has divisions. But because when I came from Princeton, I had a joint appointment. I insisted on a joint appointment, and so that was the title that was arrived at.
Now, in terms of administrative responsibilities, I understand it's one division chair, but are there two faculty committees that you sit on, two tenure committees that you've sat on?
Well, again, the tenure committees are divisional. So all mathematicians are invited to the tenure committees for physics, astronomy, as well as mathematics. There was a decision, I think, made quite a while ago, I'm not sure how early, but before I came to Caltech, that to avoid overwhelming the mathematicians, because mathematics is a small part of the division of physics, mathematics, and astronomy, only the theoretical physicists and mathematicians and astrophysicists are invited to the math tenure meetings. But even if I were just a professor of physics, I would be invited to meetings in both. And even if I were just a professor of mathematics, I'd be invited. So in that sense, it's no different. Teaching, in principle, it could be either. And at Princeton, my teaching load was one course in math and a half course in physics, because the physics load was half of what it was in math. And at Caltech, I've done all my teaching essentially in mathematics, but that didn't have to be that way. But it was decided because there were fewer math faculty and more need for mathematical teachers that I should be teaching math courses.
Barry, what about in terms of all of the graduate students and mentees that you've had over the course of your career?
So I think that if I go back and look at official majors, right? So the bulk of my graduate students at Caltech have been in math, but probably roughly a third were officially, or a quarter maybe, were officially in physics. Some of them wound up with jobs in physics departments. They were more earlier in my career somehow. One of my graduate students tells the story. He was a physics student who decided he didn't want to do mathematical physics. And when he came and said he wanted to work with me, I was a little concerned because in physics, most of the students are supported from grants, but there really is not that much term time support in mathematics. So there is almost all teaching in mathematics. And since he was a physics graduate student, he wouldn't do that. And I said he should check that it might be difficult. And he went to see his advisor at the time, who told him, Simon did Barry's phase, so he's a physicist. You can certainly work with him. We'll find out a way to support him. And the student tells the story that he was very confused because he'd never heard of something being named after someone's first name, because, of course, he didn't hear Barry's phase. He heard Barry's phase.
Barry, going emeritus in 2016, is there any significant to that year in particular, perhaps turning 70 years old?
So this may have to be off the record, because Caltech has an arrangement to encourage people to retire, but I'm not sure it's public. So I tell you, and you may have to edit it out.
Certainly.
But Caltech essentially bribes people to retire before age 70. So you can basically, by signing something saying I agree to retire in 2 years, I get 2 years total leave with no responsibility. So in some sense, you retire and get 2 years of pay before you have to start taking retirement. And it turns out, I think I was told roughly 75% of the Caltech faculty take the bribe, almost all at the last minute. You can do it between ages 62 and 70, and almost everyone does it. So they're finishing at age 70.
Barry, last question as it relates specifically to your title. Being named IBM professor in 1984, I'm curious if you ever thought about potential controversies related to IBM's alleged work with the Germans during World War II.
Okay, so that was essentially totally unknown, I think, until the last 10 years, roughly.
Yeah.
It wasn't that it was hidden, but no one talked about it. So I certainly didn't know about it. It's sort of strange because it always puzzled me that IBM made absolutely no attempt to make any contact with me. The history is that Thomas Watson Jr., the one who essentially turned IBM from a relatively small typewriter company into the IBM that we know, was on the Caltech Board of Trustees for about a dozen years. And I think he's the one who arranged the endowment in about 1960. And the only person who held it before me was Marshall Hall, who was probably Caltech's most distinguished mathematician in that era. And after he retired, the position was actually open for several years because the idea was to use it to recruit a superstar. So we actually made offers with my concurrence. I was very involved in hiring then, to 2 Fields medalists, both of whom turned us down. Basically, people roughly my age. They were very good, still very well known. And then at some point it was decided, well, we're not doing it for that, we'll appoint you. And at some point about 3 years ago, a new vice president for IBM's educational division took over. And they suddenly realized that, there seemed to be these IBM professors. And they had no way of figuring out who or where they were because they had the internal records were so bad. So they actually used Google to try to search for IBM professor, and they located some of us. They actually missed probably the most famous. So Jean Bourgain was at the Institute for Advanced Study, the von Neumann IBM professor. And so because it was called the von Neumann IBM professor, they missed it when they just searched for IBM professor. And Netz Katz, who's the current IBM professor, actually told them about it. And they had one meeting of us where they just talked to us and wanted to see about making some kind of connection, but there was no real attempt to make contact until then. I found it very strange.
I'm not sure if you're aware, but when the renaming report came out last year, there was an investigation.
I am. And that Watson was, I think it was, I read it as
Watson's okay.
We're not sure enough. There's probably some case, but it's not strong enough for us to take action at this point.
And for you, I mean, when this information came out about IBM, there was the book, of course, IBM and the Holocaust. In light of the fact that, for example, somebody like Ed Stolper gave up the Millikan name after last year, did you ever give thought to renouncing the IBM professorship?
No, absolutely not, because so particularly in the IBM case, it's not central to what IBM has done. It had nothing to do with why they gave the money. And so it wouldn't have occurred to me. I didn't realize Stolper had a choice. I thought that the Institute decided that, right, as when I went out to have my pictures taken this week, I saw the building that I referred to as the library formerly known as Millikan. I thought Caltech made a decision that Millikan's name couldn't be used. So if Ed wanted to keep the name, he could have. I would have thought he couldn't. It was Caltech policy. And if Caltech had said that I'd have to remove IBM, I would have said, it's your chair. You do what you need to do.
Yeah,
but
yeah.
It never occurred to me to renounce it. While I think there's more justification for Millikan, I really do not approve. Caltech is Caltech because of Millikan. I agree that what Millikan said, or committees he served on, but there's no sign of his having made many actions. And it's just crazy because Caltech is Caltech because of him. I mean, even Woodrow Wilson, who was, not as president of Princeton, but as president of the U.S., took actions that are reprehensible, given that Princeton became a research institution before. I have mixed feelings, but there at least you look at the balance, it's close, and I can understand unnaming Wilson. I definitely do not approve of what Caltech did. I thought to do it, and I think I did send a letter of protest to the president. I wasn't expecting, but I just thought it was wrong. I think
Barry,
these are complicated issues.
These are very
Caltech. Caltech is what it is because of Millikan. It's not that he's a minor figure. He made Caltech what it is.
And is it particularly significant to you that Millikan, even if he held some anti-Semitic views, that didn't stop him from going after Jewish professors who were of the highest ranking?
Well, but it did. At least the story I heard, and I've never been able to verify it, but the story I heard, I can't remember from whom. I actually asked Judy, and she said, well, she wasn't sure. But I heard a story that Norbert Wiener really wanted to come to Caltech in the 30s. And Millikan said, in an important area like physics, where I hired Epstein, I'll certainly be willing to hire a Jew, but I'll be damned if I'll hire a Jewish mathematician. Which is it says something about Caltech's attitude towards mathematics.
So he was doubly bigoted towards Jews and mathematicians.
Correct.
Barry, to go back to going emeritus in 2016, just as a snapshot of what you've been doing in the research world in the last 5 years, to what extent did going emeritus and unburdening yourself of committee work and advisory work and teaching, in what ways perhaps did that increase your bandwidth to just focus on the research most important to you?
Well, I focused more, but you get a little older, you slow down a little. I was always noted for my incredible energy, he said modestly, and so I still have a lot of energy compared to my peers, but not compared to, right? And there are periods in the late 70s and 80s that I wrote 25 papers in a year. But I've had, I'm trying to remember, the 5-volume series of books So you see, you say going emeritus in 2016, but it's actually 2014 because I had these 2 years before that. And so the first thing I did is actually finish up this set of 5 volumes, comprehensive course in analysis. It's what it's called. And I have one other book that I published since then and one that I'm working on, but I've slowed down a little. But as I said, you get older.
Now, in those most voluminous periods of productivity, 40 years ago, 30 years ago, in what ways do you ascribe theoretical physics and mathematics, the productivity, as a source of mental energy and as a source of physical energy?
So it's not physical; it's really mental energy. It's that I could juggle lots of balls in the air and think about lots of different things. And one of my strengths is I'm very fast. One of my weaknesses is that I'm not often patient enough. I can't solve a problem. I usually give it up. That's why one of the papers I'm proudest of, although it's not my most significant, is one that's some subject that I kept coming back to every year or two and finally cracked an idea I had. And it's just that, I proved to myself I could, but I've always been quick.
Barry, is there a place for wisdom in mathematical physics where that serves as an asset, even if your energy wanes over time?
Well, it's not so much wisdom, it's experience. And of course, the difference between wisdom and experience is not so easy to distinguish. But one of the things that I'm particularly good at, and have always been good at, is finding connections between different ideas, sometimes that don't look related at all. And the more ideas you've been familiar with in the past, the more it can help you. So there's no question, experience helps. On the other hand, there's also true. Mathematicians have a reputation of doing their best work when they're young, partly because having a fresh point of view seems to be very important.
Barry, we can now turn to mathematical physics. This is a question I've been waiting to ask. I got 3 different answers from Elliot Lieb and Joel Leibowitz and Albert Schwartz. First of all, is the term mathematical physics and physical mathematics, are they interchangeable? Have you heard of physical mathematics, or are they different?
So I've heard people use it, but I've never understood how it is intended as a different term. And of course, historically, mathematical physics, right? If you in parts of England, mathematical physics is just another name for theoretical physics. Mm-hmm, mm-hmm. But I come from the Whiteman school, and Whiteman. What was notable about Whiteman was he really believed in proving things. And to me, that's what distinguishes theoretical physics from mathematical physics. Mathematical physicists really prove things in the sense that mathematicians use proof. And theoretical physicists demonstrate things. Mark Kotz had this joke about what's, the difference between a proof and a demonstration. Is a demonstration convinces a reasonable man and a proof convinces a stubborn man.
That's a great line.
It is. Mark was a great he really was. He was remarkable person with lots of stories and jokes.
So for you, then, it sounds like mathematical physics is its own distinct field. It's more than being simply interdisciplinary between math and physics.
Absolutely. And there are certainly mathematical physicists, or people who are sometimes called mathematical physicists, who sometimes put their mathematical physics hat aside and write a paper that doesn't really prove things. But to me, it's a different field, and it often, some physicists will say what we do just, worrying about minutia of things that we all know are true. And even there, Arthur Whiteman would say there's a point in intellectual honesty that's important to even prove things that everyone understands must be true. But there have been new insights that have come from people who approach things from this rigorous point of view.
So from that perspective, Barry, coming from the idea that mathematical physics is a discrete field, what are some of the hallmarks that make it discrete? Either by methodology, philosophy, teaching, perspective, what are the things that make it distinct?
Well, as I already said, the real thing that makes it distinct is that you go and prove things. That's it isn't enough just to convince other people in the field that it's true. You have to actually have a quote proof. Now, of course, there are all these issues that the logicians like to talk about that really don't prove things because this or that axiom. But there is an understanding, at least in the mathematical community, about what a proof is. And to me, mathematical physics involves proving things.
And then this is to say that if I were to try to pigeonhole you, if you're really a mathematician or you're really a physicist, you would reject the premise of the question.
No, not totally. I'd say I have the head of a mathematician and the heart of a physicist.
What's some research that you've done that really exemplifies that idea?
Well, if I want to emphasize the heart of the physics, I should talk about something that really has had an impact on physics, because a lot of the stuff that we do, many physicists will say, is of course, it's the Berry's phase is the most celebrated in the general physics community. And it's actually quite far from in some ways, from much of my other work, and that much of my other work mathematically is connected with analysis, particularly functional analysis and operator theory, and the Berry's phase is connected with topology.
If physicists are aiming for a so-called grand unified theory, a theory of everything, and then when I ask mathematicians if they are searching for a grand unified theory and they say no, as a mathematical physicist, how do you square that circle? If math can be understood as the language of physics.
So grand unified theory is just, at least in my understanding, is just the question of trying to put together gravity with strong, weak interaction. That's, mathematicians would like to understand that too, but in some sense, mathematical physicists, at least my kind, are really looking to make sense out of frameworks that already exist. It wasn't mathematical physics to invent quantum mechanics, but it was mathematical physics to prove that atomic Hamiltonians are self-adjoint. So it would be folly to expect that you would find your first attempt to actually unify, if we ever do that, would be done on a mathematically rigorous basis. It's not going to happen. Doesn't mean if I happen to have a good idea about doing the unification, I'd say, well, it's not going to be rigorous, so I can't do it. But it's not what I'm searching for.
Why is it not going to happen rigorously?
Oh, it might eventually, but it's a first stage. It's crazy. In some sense, it's not that I say it won't happen eventually rigorously. In fact, it should. I'm just saying that the idea of saying, I'm not going to worry about the details of doing things totally rigorously. I'm going to throw away that and wave my hands. And if it's reasonable, I'll plow on, is in fact the way you make progress at a certain fundamental level. And so, right, the people, it's a different kind of working to make progress at this sort of, I mean, the people, we still don't really have a mathematically rigorous formulation of electroweak or even, let alone strong interactions. The quantum field theory is not mathematically rigorous in 4 dimensions. It's one of the big problems. It's a very interesting one.
What accounts for this shortcoming? What explains it?
It's hard. It's not. So one of the areas I worked in was called constructive quantum field theory, and it was probably the hottest area in mathematical physics in the early 70s. And a significant fraction of my efforts was in that area. And at the time we were doing it, we knew that the ideas we were working on seemed very promising in 2 and 3 dimensions, but there would have to be a very good idea to do 4 dimensions. Technically, it has to do with the fact that whether a theory is super renormalizable or just renormalizable. Super renormalizable means there are only finitely many counter terms, and you could sort of with your bare hands do the renormalization. And we were very successful in that. It was always understood you'd need some really good idea to go to the next phase. And some of those good ideas probably have to do with the renormalization group, which was invented just about that time by physicists, but really pushed through later. But no one has figured out how to do it. It was at the time clear you'd need a really good idea. Nobody, it's 45 years later, and nobody's had a good idea.
Barry, 2 questions that highlight an academic divide between physics and math. First, coming from physicists to math, and then vice versa. So just to take one of many examples, when certain physicists are critical of string theory because it has no basis in observation or in nature so far as we can tell, and the basis of the dismissiveness is, well, that's essentially just mathematics. In couching it in those terms, what's your perspective on that? On physicists dismissing it because it's quote unquote just mathematics?
Well, of course, from my point of view, it's not mathematics either.
Okay.
Because it really is, it's speculative theoretical physics. It's not, they're still searching for a framework. To do real mathematics, you have to have a framework. You can't, if you don't, no, there has not been a precise mathematical definition of string theory. It's one of the big issues. It's one of the hard problems that string theorists haven't solved. They've only been working on it for 20 years, but they feel they're getting closer. But there's no, at least in quantum field theory, there is something very close to a precise framework, even though we don't know. Whereas in string theory, they're not quite there yet. So it's in some sense neither physics nor mathematics.
I wonder if you've sparred with John Schwartz over the years on these things.
No, absolutely not. John and I have had little contact. We have just such different views of the world. Witten and I might conceivably, but we haven't. It's just, I haven't. One of the things I don't like to do, although I just did sort of, is spout off about subjects I don't feel I understand very deeply. And I don't really think I understand string theory very deeply. I just have seen little bits and pieces enough to know they don't really have a mathematical framework yet, although there are mathematical questions that arise in the subject that are well-defined mathematical questions that people have made progress on. But no, I have not sparred with John.
To the extent that you have a sense or an intuition about where things might be headed, feelings about string theory have material consequences in faculty hires, in terms of funding decisions. So are you of the opinion more that string theory deserves more support, that it deserves more nurturing because it might get to where it wants to go? Or are you more of the school where you don't really have patience with this because they haven't demonstrated it in, the 40 years since the early 1970s?
So I tend to be very suspicious of overpopulated fields. And I tend to think too much money goes into these overpopulated fields. But I've never had to make funding decisions, and I'm not about to pontificate on the subject.
Okay.
I do share some people's unease with the current state of theoretical physics, that it seems to be focusing too much on things that are not close enough to experiment.
What then?
Both parts of string theory and also parts of quantum computing.
What then, if not string theory, might get us closer to a quantum theory of gravity?
I don't know.
Yeah.
I understand. The issue is, if a field isn't ripe, then does it make sense that you're sending a large fraction of your bright young people into it? I don't know. It's an important field. So yeah, you send all these soldiers and let them, but it's again, I have my own relatively well-prescribed areas that I've worked in, and I tend my garden and don't really worry about. And at least because of my administrative responsibilities at Caltech have been more mathematical, I don't worry too much about this.
Now, to ask the question going the other way, for pure mathematicians who are not at all interested in relating their work to physical reality. So for you, for all of the mathematics that you do, is there always some connecting point to observation or experimentation?
Certainly not. In fact, in the last 15 years, I've been doing things that are not really mathematical physics. They're so the kind of mathematical physics I do is very much connected with what's called spectral theory sometimes, which you would think, a spectrum, that has to do with light, but in fact the amazing thing, although it is connected to light, is that, as far as I can tell historically, it comes from the spectra of operators. And I don't believe that whoever invented that name, and it was probably someone in Hilbert School, knew that they certainly didn't expect that it had any connection to spectra in the sense that you see when you look at light from the sun. But it's called spectral theory. And I sort of wound up looking at problems connected with the theory of orthogonal polynomials that they really are totally disconnected from physics, except to the extent that if you get some insight of one part of spectral theory, it may give you have feedback to some other part of spectral theory that, because of my experience, I know is connected to mathematical physics. But it's certainly not true that I've essentially let my I've random walked in areas of mathematics sort of towards, with its directed random walk towards those parts that are suggested by more the mathematics than the physics. And so I've actually wound up for the last few years doing most of what I do is not that connected with physics, although the current book I'm writing is going back to some things in statistical mechanics, which have much more of a connection to physics. But much of the research I've done in the last 15 or 20 years is in this spectral theory of orthogonal polynomials. And there certainly are some mathematical physicists who disapprove of my path in life because I've stopped doing what they regard as important.
Barry, just as a snapshot in time, circa November 2021, and as a way to convey to an audience of non-specialists for whom your work is rather obscure or it's difficult to comprehend, just on a workaday basis, what does a day look like for you? Are you on the computer? Is it a pen and pad? Is it big thoughts staring up at the sky? How do you do your work?
So now much of what I'm doing is actually worrying about this book. So it's almost entirely on the computer, either looking at papers. So this is a sort of comprehensive look at the mathematical rigorous theory of phase transitions. Mm-hmm. And there were certain results I know are around. I never quite understood the details of the proof, so I have to first understand it and then figure out the right way of exposing it in the context of this book, fitting in with other parts of the book. And so it's a lot of work on the computer and teching. Although I'm unusual in that I only learned to tech about 5 or 6 years ago. So I had the world's greatest secretary for many years. And she unfortunately passed away from cancer in probably 2015 or 16. And Caltech actually paid someone to finish the teching of my this 5-volume work, but part of the deal was I was going to teach myself enough tech that after in the future I could do my own teching. So I've learned how to tech, and so part of it is that, but it's, and you know, I'm now retired, so I don't feel this. So one of the nice things about being retired is I can tell people I no longer write letters of recommendation. There are a lot of tasks that are important, but I feel I don't have to do anymore.
Barry, as you say, this walk that you've been on in the past 15 years, is this book project a culmination of those efforts?
Not at all. It's total. It's really going back. So much of the group of people that is in my area focus not on, you know, if you look at what mathematical physics in a reasonable sense means, one part of it is, say, general relativity. But I've never thought about that, and most of the people I've worked with have never thought about it. So there's sort of this core area that maybe goes back to Whiteman of non-relativistic quantum mechanics, quantum field theory, and statistical mechanics, done mathematically rigorously. And my central area has in many ways always been non-relativistic quantum mechanics. And when I came to Caltech, much of my work focused on those areas and the orthogonal polynomial physics. But when I was at Princeton in the late 70s, I gave some courses in rigorous statistical mechanics. I started writing a book that turned out was going to be a 2-volume work. One of it was finally finished. That's sort of more formalism and all the fun stuff isn't in it. Was published about 1990. It was finished up just after I came to Caltech. And the second volume I never wrote. And a couple of years ago, some people began to really have a campaign that I really should go back and write this book I promised.
What are your goals once it's published? What do you hope it will accomplish?
This is an area, so it's a little surprising. This is an area that there was really a golden age in the 70s and 80s. There have been some progress since then. But there really has not, there have been a couple of books that are not bad, but they're not as comprehensive as I'd like. And the goal is to make this area accessible. There are a lot of people who do things connected with it, easy model, things like that. I want them to have a decent reference.
Barry, to take a very broad view of your contributions and impacts, particularly in light of the idea that mathematical physics is its own discrete field. So in all of your major accomplishments, where have you had the most impact in physics? Where have you had the most impact in math? And where have you had the most impact within your own field, the garden that you've tended to, mathematical physics?
So there's no question that in physics, it's the Berry's phase stuff that has had the greatest impact. There are some things that mathematical physicists actually did first that theoretical physicists then rediscovered and sort of forgot that we'd done it. So, for example, lattice field theories, everyone will say it's due to Wilson. And in fact, and Wilson did do it in a much broader framework, but for boson field theories, 2 years before Wilson's work, where Rosen and I did it, but nobody noticed it. So did it have impact on physics? I don't know. You're the historian of science. How do you determine things that, historians of science, of course, have to worry more about, Gauss is something that was in Gauss' notebook, but was only rediscovered, and that's how people found it. How much credit does Gauss get? How much credit do we get? But there's no question that the biggest impact is this Berry's phase. Not because Berry's phase itself is so important, but I introduced these topological ideas that have become very important. Surprising, I think, both Berry, me, and many other people. So that's certainly the area that's had the largest impact.
Could you explain Berry's phase a little bit, what it is?
Okay, so let me back up a little bit before that because it's part of a bigger picture. So there's something called the quantum Hall effect. This is the discovery that it doesn't matter what it is, but some object is quantized that people hadn't expected to be quantized. And in fact, it turns out the best measurement of the fine structure constant is in terms of the measurements of this quantum Hall effect. And in the early, so there have been probably 3 or 4 Nobel Prizes connected with the quantum Hall effect. The first were the experimental discovery, and then there were several theoretical things. And in the early 1980s, a theoretical physicist named David Thowles, who spent he's British, but he spent most of his career in Washington, found an explanation in terms of, he computed some integrals, which he was able by hook and by crook to see were quantized. And I had a postdoc at the time. He actually wasn't a postdoc. He was more than a postdoc. He was officially only a postdoc at Caltech, but he'd been an assistant professor at Princeton. He was one of the people that sort of came with me as part of the deal. He got very interested in the quantum Hall effect and read about Thowles's paper. And he came into my office and we talked about it some. And we realized that this was basically, so in topology, there are certain things that are naturally quantized. So the number of times you wind around is an integer number of times. It's a natural integer. And we realized that really what Thowles had discovered were the integers that he found were really what are called homotopy invariants. And we wrote a physical review letter. We actually first tried to say, oh, well, once we know they're homotopy invariants, there's sometimes other homotopy invariants. Maybe there's some other homotopy invariants around that we would find a new interesting integer. And the first thing we found is that in the particular topological object that seemed to be underlying there were no other topological invariants other than the ones Thowles had found. So that was the main point of this physical review letter, although in retrospect, what we should have made a bigger deal of is we should have said, hey, this is topological, because that's the big realization. And this was probably, so let me just think, this was probably, I may have the year, I think it must have been early 1983. And in the summer of 1983, I was invited to visit a mathematical physicist in Canberra, originally Irish guy who was then in France and wound up in Australia. And while I was there, I met Michael Berry a couple of times, and he gave a lecture that I actually hadn't realized he was there. It was in physics. I was visiting mathematics, but I'd heard he'd given this lecture, and but I missed the lectures, but I went to see him, and he was very kind and explained to me what he'd found. And what he'd found, so there's a theorem in quantum mechanics called the adiabatic theorem that goes back to the earliest days of quantum mechanics. It was found by Fock in about 1930. And the first real mathematical understanding was by Kato in 1950, roughly. And what it really says is if you, in quantum mechanics, do something, if you have a time-dependent phenomena and you start out in a eigenstate, if that isn't too technical, of the Hamiltonian, and your Hamiltonian varies, and you do it slowly enough, you stay in an eigenstate.
What does slowly enough mean?
Well, what it mathematically means is you put in a time scale, and slowly enough means you talk about what happens in the limit as t goes to infinity. And Barry became interested in what happens when you do, well, he was actually originally doing it in perturbation theory, not with a time dependence, but just where you were varying a parameter and just seeing how eigenstates varied. And he first made the discovery that if you're looking at real matrices and you go around a singularity, you come back, the eigenfunctions flip sign. And he gave a talk somewhere and someone said, well, what if it's complex? He said, oh, it's the same answer. And then he thought about it some more and realized, no, there's a possible phase. And it was more natural than to do it in perturbation theory, to do this thing adiabatically. And what happened is, so if you do it and you do the naive calculation that you might expect in the adiabatic theorem, there's some natural term that grows linearly in this time, which is going to infinity, but might happen to be zero. But on top of that, there's a finite leftover piece. And he did a calculation of what the leftover piece is. And that was what he told me. And my immediate reaction was, this could have something to do with Foulis. He said, oh yeah, Bernard Souillard. So Bernard Souillard is a French mathematical physicist who actually left academics a couple of years later, became a business consultant. But he said, yes, Souillard, when he heard this, told me the same thing. So I asked Foulis, and Foulis said, no, there's no connection. I said, well, let me think about it. And essentially that night I figured everything out because I'd already been thinking about it. It turns out to be incredibly connected to what Foulis had done. So to try to give you the connection, let me go back and talk about a simpler thing. So let's imagine the geometry of a sphere, which is curved. So one of the things that Gauss discovered, and that was generalized by Binet, it's called the Gauss-Binet theorem. There's a rather remarkable fact if you sort of take the sphere. So there's a natural notion called curvature, the curvature of the sphere. The more tightly curved it is, the larger the curvature is. And it normally varies over the surface, but of course for a sphere, it looks the same everywhere. So if you actually take a round sphere, the curvature of the sphere is 1 over r squared. You integrate that over the sphere, that's 4 pi r squared times 1 over r squared, you get 4 pi. And what Gauss essentially discovered is, well, if you deform the sphere, you again have a curvature. Now, if you integrate it over the whole sphere, you always get 4 pi. It really just depends on the topology of the surface. And then if you do it for a torus, you always get 0. And this is, in fact, what you get is what's sometimes called the Euler-Poincaré characteristic of the surface. It's a topological invariant that you get by integrating the curvature. And what Avron and Zierler and I had essentially realized is that what Foulis was calculating, although we didn't quite have at that time, and my Barry's phase paper first used the term curvature, but what we realized in the meantime is that there's a natural geometric object in the infinite dimensional set of quantum mechanical states that has a curvature. When you integrate it, just like when you do it over the sphere, you get 4 pi times an integer. You always get something times an integer, and that integer is this Foulis integer that describes the quantum Hall effect. Okay. Now, in terms of curvature, there's a different idea. It's called holonomy. It also actually, I think, goes back to Gauss. So suppose you take a sphere, and what I'm going to do is the following experiment. I'm going to walk on the sphere carrying a spear, and I'm going to do my best to keep the spear always pointing in the same direction. Not the direction I'm moving, but the direction it was. So I imagine starting along the equator, going a quarter of the way around, up to the North Pole, and then down back to where I started. So I do that. I start being parallel to the equator, keep being parallel. Now I turn, but I don't turn the spear. As I walk along towards the North Pole, the spear is pointing to my right because it started out pointing along the equator. I turn, but it doesn't. It's to my right. It keeps going to my right. Now I go back to now I go to the North Pole. I turn again. And if you think about it, if it's exactly 90 degrees, I'm going to be pointing down in this other direction. And when I come back, even though I've done my best to keep it parallel, it's going to have been rotated by 90 degrees, which in terms of radians is pi over 2, which is exactly the integral of the curvature over the eighth of the sphere that I've looked at. So the holonomy is also an integral of the curvature, but instead of over the whole surface, it's over part of the surface. And what I realized is that Berry's phase was exactly holonomy in this topological sense. And it was the same, there was the same underlying curvature. And so I wrote a paper where I coined the phrase Berry's phase. And I must admit that I'm a little annoyed that while Berry's phase is a great name, the underlying curvature is called Berry's curvature, even though he had no idea it was a curvature. He did have a formula in his paper for what is the Berry's curvature, but it was...
It should be Simon's curvature?
Well, perhaps. But it certainly is it's my curvature. It's not his curvature.
Barry, to get back to the question of impact.
Well, and to finish the story.
Yeah.
And he actually published his paper. It was actually appeared after my paper. But he published it in the Proceedings of the Royal Society, which despite its impressive name and history, people don't normally look at. But I published my paper in Physical Review Letters. And literally, there were probably 500 papers written on this within the next year.
Yeah.
The reason has nothing to do with its intrinsic interest, I think, but it has to do with the fact that everybody's supposed to understand the adiabatic theorem. You learn about it in quantum mechanics, in the first quantum mechanics course. But there was some new facet of it that was there, and everyone had to write a paper on how, I understand that because it just is the adiabatic theorem. And at the time I regarded this, the excitement was a bit of a curiosity, but then some serious condensed matter theorists began to realize, if there are these topological invariants here, they must be all over the place. And it's become a major part of condensed matter physics. That is called topological distinction between different matters, different types of states of matter are called topological phases because they're distinguished by having different topological invariants. And it really is a case where neither Berry or I understood that we had found something that was going to be really important. It was a very cute piece of mathematics, but it's been very important because it's been very useful and because it introduced ideas. And one of the reasons I also think it caught on is these ideas were at the time had become, within a year or two earlier, had become very important in the study of gauge theories. And so a lot of elementary particle physicists were very excited because suddenly there were these, and so people became interested because somehow there was at a mathematical level, a connection between what they were doing and condensed matter physics. And it's one of the reasons I think it's become so important and natural. And it was not something I think we realized at the time. That's certainly the piece. That's certainly the piece that's had the biggest impact on physics.
Has it gone beyond condensed matter theory? Where else do we see it in physics now?
No, as far as I know, some of the underlying ideas are, of course, central to, and were central before we did it, to ideas in quantum field theory. But it's not. It's as far as I know, it's really only in condensed matter physics, but it really is a major part of condensed matter physics now, is the study of these topological phases.
And to turn to that aspect of the question of contributions in mathematics for mathematicians who might not have your physicist sensibilities.
So probably what I'm best known for to people outside of the field of mathematical physics is, along the way, I got involved in various techniques, mathematical techniques, and I wrote sort of the definitive. So I, for example, have, he said immodestly, the definitive book on what are called trace ideals, which are certain ideals of operators that are very important in many areas of mathematics, and have become very important in quantum computing. Again, not because I was doing anything connect, but so I often, well, I'm not around that, but in the couple of years before I retired, I'd often have postdocs from Fresco's group coming out and ask me some questions that were connected with things and then within mathematical physics, there are discrete. There are both specific contributions, but also one of the things that I was fortunate is I was often working, one of the first people to work in some sub area. I very much enjoy finding an area with lots of low-hanging fruit. And so, right, there's an area there, and there are some things that have now become, there are people who do nothing but that, and there are conferences just in that area. So you look at the theory of almost periodic, so-called almost periodic Schrodinger operators. And it's a huge area that lots of mathematicians have become interested in because it is such an interesting and beautiful subject. And Avron and I wrote some of the basic papers in that, actually about the same time we did this work on various phase. But there also are, Lieb and I did work on understanding the quantum mechanics of large atoms. Where we realized Thomas Fermi was exact in a certain limit that is surprising, and again led to whole industries.
Barry, if we can imagine a table of contents for your research career where, the rough dates for each chapter would be your graduate school years, your early faculty years, your middle faculty years, the transition to Caltech, later faculty years, and now in retirement. How many chapters would there be if you look at the major topics that you've worked on going all the way back to your graduate school days?
Well, because if you looked at it, I sent you a paper called 12 Tales in Mathematical Physics.
There you go.
However, that stopped, in some sense, about the period when that stopped about the area of 2000, 2005, when I shifted to this spectral theory of orthogonal polynomials, and there would presumably be a 13th chapter. But that's, it's a somewhat artificial way of dividing things, because it made sense but one could make it, the fact that it's exactly 13 is, because in some sense you could say quantum field theory, statistical mechanics, and non-relativistic quantum mechanics. You could also say in non-relativistic quantum mechanics, the many-body, and then the almost periodic and random. So it's not clear how, right? But
so on that point, what have been the commonalities or the research areas that you've always remained close to, and where have your research taken on truly new dimensions, truly new directions?
So in some ways, the 13 chapters really do represent different directions, where the beginning of that chapter is a sort of new direction. Well, I call in the 12 chapters, in the 12 tales, there's the almost periodic and random are separate. They really are two facets of a half piece. But basically, when I first came to Caltech, I told Yossi, Avron, who was working with me, I said, a lot of the things that we've been thinking about have sort of wound down. We really need to think about what some new area to look at. And I said, why don't I think about it, and we'll come and talk about it. And I came back and said, well, there seem to be two really sort of interesting things to think about. One is this almost periodic, where there was beginning to be a little work, and certain things about quasi-classical limits that there clearly were new mathematical directions for. And I said, it looks like this almost periodic isn't very hard. We can probably wipe that out in 6 months. So why don't we do that first, and then we'll get to the other one. And in fact, the almost periodic has become a huge industry. I was working on it as my main focus for probably 10 years. Wasn't 6 months at all. And I never really did get to these I did do some quasi-classical things, but not what we were talking about then, and there's been a lot of interesting work in that area, but not by me since then. So there was definitely that I regard as a new direction. But generally, if you ask about this shift to orthogonal polynomials, it really was because there was a natural question that I was looking at with my students, and we realized that it was connected to the orthogonal polynomials, and it sort of led naturally. So most of my shifts have been really just where the research led me. And it's not that I sort of, I'm not one of these people who, I'm sick and tired of doing this. It's where one piece of research leads, and in retrospect, you realize you've turned a corner. But it's more that than...
Barry, what are the feedback mechanisms that you've used? As you say, when a particular field is winding down and it's time for something new, when does that mean achieving a breakthrough? When does it mean you've intellectually tired of this area? And when does it mean that the field is saturated and you just want to go into a new area?
Okay, so I actually can't think of any time that I've left an area because I felt it was saturated. Generally, it's because, as I said, I find the low-hanging fruit, and what's left looks really hard, and you think about it for a little while, and you decide, it's probably time to look for another orchard with low-hanging fruit. So that's what this example of shifting. It's not that the areas that in fact, there's no question that one of the areas that I've been thinking a lot about in my career, but particularly from my late graduate student days till 1985 or so that's 15, 20 years almost, is the theory of n-body quantum mechanics, particularly n-body scattering. And someone who made some of the greatest discoveries in the understanding of two-body scattering, Israeli mathematician named Shmuel Agmon, who's actually celebrating his 100th birthday next year. He said to me at one time, he said, those whom the gods would drive crazy, they teach of the problem of n-body asymptotic completeness. And it's quite clear. I know there were several people who announced solutions, and then there were errors. And this is something that I wouldn't say was a major focus because I had so many other balls in the air, but I thought hard about it and made two contributions that turned out to be important. But it was clear it was a hard problem. I didn't have any great ideas, so I wasn't going to think about it anymore. And it was, in fact, solved shortly after I left the subject by two people, one of whom had been my postdoc. It was one of my first postdocs at Caltech. After he left Caltech, he met up with someone else who had been an assistant professor at Princeton when I was there, and they solved the problem. But it's clear that it wasn't that there was nothing left. It's that the problems that were left were very hard. My temptation has been I'm not someone who says, here's a hard problem, I'm going to beat on it till it gives way. It's just not my style.
When have you had eureka moments, and how do you know you've gotten there?
Well, you don't know in mathematical physics. You don't know you've gotten there until you've actually got the proof. So there are two kinds of eureka moments. One is realizing what's probably true, and the other is figuring out how to actually prove it. And those can be separate eureka moments. So if so if I go back, I think one of the things that I mentioned before was that Elliot Lieb and I had done this work on Thomas Fermi, and that came up. So we were both visiting the IHES. Does that mean anything to you? The Institut Haute Études Scientifiques. It's a small institute in Bure-sur-Yvette, which is a suburb of Paris between Orsay and Saclay. So two big math and a physics center. And it's over the years had a lot of it. It was supposed to be the French equivalent of the Institute of Advanced Study. And so David Ruel was there, Kohn was there. There've been several math Fields medalists there. And we were both visited. David Ruel had invited both Elliot and me, who didn't know each other well. And Elliot became convinced that somehow this Thomas Fermi theory there should be some way of making real sense out of it. It was somehow an uncontrolled approximation, but it must be. And he said to me, it was something we should think about. And it just happened that I had taken as a graduate student with Arthur Whiteman a quote intermediate quantum mechanics course that was unlike any intermediate quantum mechanics course anyplace else in the world, because Arthur actually proved things and did things like prove self-jointness. And he talked about some work that had been done. He did Thomas Fermi. There wasn't much that was mathematical, but he discussed it. He talked about something called Teller's theorem that says molecules don't bind in Thomas Fermi theory. There was a paper Teller wrote in, maybe it was a Wigner birthday issue, I don't remember. And so after Elliot and I talked for a few days, I came to him and I said, Elliot, the fact that this could describe real physics can't be right because molecules don't bind. So I went back thinking, well, Elliot walks in the next day and says, Mr. Dalton's hooks are in the outer shell. And he had the idea that this quasi-classical limit which is what Thomas Fermi is, should only be true when there are lots of electrons. So if it's a good description, it should be a description of the core of atoms. And it could be a totally accurate picture of the core of atoms. And since chemistry happens in the outer shell, Mr. Dalton's hooks, it's not inconsistent that molecules don't bind. And so the first eureka moment was somehow realizing that maybe there was a real field here to look at. And the second part of this was, the first thing we had to realize is there was essentially no literature, even that these equations, which people could formally write down, actually had solutions, particularly in the molecular case. And I had just the right functional analytic background that we could do it. And not only that, I taught Elliot an enormous amount of techniques that he then became the great world expert on. Eventually, these minimization techniques that we needed, he's now the world leader on. And then we realized that we could sort of do this classical limit. There had been an earlier paper we knew about that did a WKB type approximation with single particles, and we realized using these techniques we could do things, except there was a problem with the fact that the Coulomb potential had a singularity. And so he was actually at IHES for the whole year. I was 3 months in Paris, 3 months in Marseille, and 3 months in Zurich. And so I left for Marseille, and we had left what we called pulling the poison Coulomb tooth. And we didn't have a result. We had an interesting result if it was cut off, but it wasn't the result one really wanted. And I came back for a long weekend to Paris, stayed for Shabbos with Chaim Brazis. And then Elliot and I worked for a few days, and we realized what we needed. That was a eureka moment, too. Nowadays, one would, in fact, use the Lieb-Tiering inequalities to do it even easier. It was a special case of Lieb-Tiering, but we didn't understand it in those terms. Of course, Lieb-Tiering didn't exist then. And there was a eureka moment there when we realized we had the full result. And I guess the punchline of this whole, well, there are two punchlines. One is, so we wrote a physical review letter, which we sent in, and we got a referee's report back that clearly had been written by someone who worked on Thomas Fermi in the 1930s, that read, "This is the worst paper I have ever seen. It is a sequence of unproven assertions," which is correct. It was an announcement, many of which are obviously false. For example, the authors assert that the Thomas Fermi density is C super infinity, which would make the density identically 0, 1, or infinity, depending on the value of C. Of course, totally misunderstanding the notation C super infinity. Elliot and I were at a conference that next summer in Copenhagen when we got the report. I wanted to make a big deal about the guy not understanding notation, but he focused on some physical things. We demanded a second referee. I'd heard Freeman Dyson was the second referee, and he got a big kick out of the referee's report. He was accepted. And the second punchline is that this fact that molecules don't bind to Thomas Fermi turned out to be the key to Elliot's work with Tiering on stability of matter. Because the idea that when you have lots of electrons and protons, that matter doesn't collapse is connected with the fact that they were able to control quantum mechanics rigorously using what were essentially the first Lieb-Tiering inequalities by Thomas Fermi, and then used the fact that in Thomas Fermi, you had stability of matter because molecules didn't bind. So I was really wrong when I said that Thomas Fermi couldn't make sense because of Kelly's theorem.
Barry, in the way that physics has such well-defined grand mysteries or puzzles or whatever you want to call them, as we talked about merging relativity and quantum mechanics, looking for physics beyond the standard model, understanding the conditions at the Big Bang, you name it. Does mathematical physics have its own distinct and well-defined grand mysteries or puzzles?
Well, I wouldn't say they're necessarily grand, but because they've been open for a long time, they become important open problems. So I have several famous lists of problems, of open problems. If you look on Wikipedia, you will find an entry called Simon's problems. They don't have anything like the grandness of of merging quantum mechanics, but they're puzzles. So one of the to me most interesting open problems involves the work that first Froelich, Spencer, and I did on classical Heisenberg, and then Lieb, Dyson, and I did on quantum Heisenberg. So one of the most important ideas in physics is the idea of spontaneously broken continuous symmetries. It's responsible for Higgs bosons, and it's an absolutely central element. And if you ask, has it been rigorously proven? Well, obviously not in quantum field theory, because I said earlier that four-dimensional quantum field theory we don't even know makes sense. So how can we prove, although in lower dimensional quantum field theory there is an analog and there are results, but essentially the only result so Froelich, Spencer, and I found a way of proving that that continuous symmetries are broken in two-dimensional discrete lattice models of classical models, where you have spins on spheres. And then Dyson, Lieb, and I, as a follow-up, asked what about the corresponding quantum models? And there's the ferromagnet and the antiferromagnet. Everyone believed that the antiferromagnet was much harder because its ground states is not exactly known. The ferromagnet was supposed to be easier, even though classically they're equivalent, but quantum mechanically they're not. And Dyson, Lieb, and I thought we found a proof for both the quantum and the ferromagnet, quantum ferromagnet, quantum antiferromagnet, wrote a physical review letter. And fortunately, before the paper was published, Jörg Froelich was teaching a course out of our preprint with the details and came to Elliot's office and said, I don't understand why such and such is true. And I looked at it and said, that's because it's not. And so basically we have a proof that works for the antiferromagnet, but the quantum antiferromagnet, which we announced, was open. And 40 years later, it's 76, it's 35 years later, it's still an open problem. It's one of them, it's an important open problem, but it's not like, combining. So there are sort of, it's true in other parts of mathematics. There are usually well-defined problems that become important, sometimes because they're really important, but often because they're interesting and lots of smart people have worked on and haven't solved them. They become important open problems. And there are lots of things like that in mathematical physics, as there are in mathematics. And sometimes they're really, really, really central, and sometimes they're just interesting. So, you'll see in Quantum Magazine, there'll be somebody's or other's conjecture has been solved. It's the Riemann hypothesis really is important because it will tell us about the structure of primes, but often these conjectures that have been around for 50 years are interesting. They're fascinating problems, but they're not of great depth, except that they've been around and are known to be hard. There are lots of things like that.
And for these puzzles that have been and remain hard, what role can computers play in solving them?
At least the problems I'm thinking about. Generally, it depends on the particular problems. The problems I would think about, like this quantum Heisenberg model that I just mentioned, ferromagnet, computers are useless. On the other hand... Because
why, Barry? They lack what? What makes them useless? They lack imagination? What is it?
The real problem is you know what you expect to be true, but you don't understand why it's true. So, and computers... Right, a computer does an algorithm. You can tell a computer to compute something, but the issue here is not that you don't know what to compute. It's that you don't know what the mechanism is. Something that you expect to be true, you don't know the mechanism that forces it to be true. And so there's no way. On the other hand, there are certain kinds of problems in combinatorics where computers can sometimes be very useful and have been useful. But not for most of these problems, computers are, at least in the current state, useless.
And of course, all of these comments are rooted in classical computing. I wonder if you are interested in following developments in quantum computing, and that may lead to new possibilities.
Well, again, there are lots of interesting things I think quantum computers can do, but not along, right? What I said, the real problem is computers aren't useful because they're algorithmic and you don't know the right computational questions to ask. The same thing is going to be true with a quantum computer. Quantum computer is, it can go much further than computers on certain kinds of problems, but it doesn't mean that it isn't basically an algorithmic machine. And lots of problems in mathematics, and many of the problems I talk about in mathematical physics are really mathematical problems. They're not problems in physics exactly, although you need some physical insight perhaps to understand what to do. But they're really, again, computers are not going to be, at least as we currently think about them now, I don't really understand enough about AI and other such things to tell you that this is, that I won't be wrong. I'm an old guy, but I in terms of computers as they currently exist, including how a quantum computer might exist, no, but it could be, AI has certain other kinds of algorithms that maybe they can do. I don't know, but Barry, not current.
Switching topics, with over 40 years of service to Caltech, some institutional history questions. The first and perhaps most fundamental for you, your research, your colleagues, with Caltech's age-old insistence to stay as small as it is, when has that been an asset to you, and when has that been a liability?
So you have to really understand, from my point of view, in areas I'm interested in physics, Caltech is not small. Caltech's physics department is as big as at, I think, any competing, and that's not true. Berkeley, any of the competing private schools. You look at Harvard, you look at Princeton, you look at Chicago, they're major physics departments. They're roughly the same size as Caltech. One of the things I noticed when I first came to Caltech is you look at all the schools I just mentioned, Harvard, Princeton, Chicago, mathematics is, if anything, slightly bigger than physics in terms of number of faculty. At Caltech, we have a third the number of mathematicians as the physics. Now, that's not totally fair because, of course, right, some people that are officially in physics here could be in astrophysics, so maybe it's only twice as large, but it's still much larger. We are a tiny mathematics department compared to our competitors.
And you're excluding applied math from this, I assume.
Correct, because applied math now has become, particularly if you now take CMS, but when I came to Caltech, there were 4 applied mathematicians. It was a very small group. There was, some of the things that I have tried, well, I gave up eventually, but I was very interested in convincing people to allow mathematics to grow with no success. There was some discussion about, there were 2 times that it was at least taken a little seriously. There were some people in engineering. So engineering and physics are by far the largest divisions. PMA and engineering and applied science are by far the largest divisions at Caltech. They're 3 times the size of any other division, or almost 3 times. And both are a little unwieldy. And there were some people in engineering who felt that it might make sense. There really were, to split engineering in 2, it was systems, and there was some discussion that we should take pure mathematics and some part of EAS and form a division of mathematical sciences. And at least twice it was at least taken seriously enough that it went besides just some faculty talking among themselves. One time it was shot down by the provost, who said, gee, if I thought about doing that, I'd have to rediagonalize the whole matrix. Right? That's not something you'd hear from administrators at most places. But it was a very Caltech way. Essentially, he said, yeah, maybe chemistry and chemical engineering should be split apart. I don't want to think about it. And it was shut down. And the other time it sort of fell over by its own weight, because in fact, there are traditionally some tensions between applied math and pure math that always come up. I had colleagues who were convinced, perhaps correctly, that it's true that dealing with physicists can be a pain, but it would be worse dealing with applied mathematicians. And so it never went anywhere. So I don't think of Caltech as being small in physics, but it's small in mathematics, and it matters. It's also meant that we tend to be a little unstable. So in the year 2000, the combination of several retirements and Tom Wolfe's untimely death meant we suddenly were from our usual size of 17 down to, I think, 11, and we were in a crisis.
When has that smallness in math been a problem for recruitment, both of faculty and graduate students?
It's always a problem in recruiting faculty. Well, almost always, because unless you have someone who says, "I do my thing, I don't want to talk to anyone," they face the fact that I faced it when I came to Caltech, right? I at Princeton, there were traditionally 3 joint appointments in math and physics. Now, actually, technically, right now, there are 4 people, I think, with joint appointments in math and physics, although the math appointments are courtesy, because the string theorists and Kitaev have joint appointments, but they're not really math. When I say joint appointments, I mean really people doing mathematical physics. I knew that I was sort of led to hope, and we did hire eventually, but it took many years. We made many offers that were turned down. I would get a second person, but I knew I'd have enough resources that I could make a viable group. But it was a major decision that I knew I was going to an institution where I wouldn't have the same kind of resources that I had. I also realized it probably would mean I would mainly be able to focus on, instead of quantum field theory and statistical mechanics and non-relativistic quantum mechanics, I mainly did things connected with non-relativistic quantum mechanics because of what would be around. So I knew that was going to be a factor. On the other hand, my wife loves Southern California.
Yeah.
And I love the idea of raising my kids here. So I made the change, but it was certainly recruiting me. It was an issue, and it's always an issue when you're trying to recruit.
Barry, is that to say that in looking around you at where the numbers are, who to collaborate with, that when you came to Caltech, you had more of a collaboration, more work in physics and less in math, just as a result of who was around?
No, because I collaborated almost all my collaborations in, at least when I was in Princeton, were with people who were specifically doing mathematical physics. Is that probably without terms of joint papers, probably, although there was some mathematical questions, I would consult someone on. At Caltech, it's again true that almost everyone I have collaborated with is quote unquote mathematical physics, except There are a couple of times there were mathematical questions that there happened to be people I could. So I have a joint paper with Wolf and an important joint paper with Makarov. It would have been as easy to have such papers at Caltech, at Princeton. It just happened the problems that brought them in didn't happen to be around. But in each case, I had a well-defined mathematical problem that I was sure they would be able to. Sure that they might be able to help me. In each case, we found something very nice.
Barry, one of the great transitions at Caltech over the course of your career in terms of the interests of undergraduates has been in the early 1980s, of course, physics was the dominant major, and today by far it's computer science. Where has math, and specifically mathematical physics, where has it been impacted over the course of this transition?
So let's talk about mathematical physics first, because there are no undergraduates doing mathematical physics. It's
by design?
Hard. Well,
there's too much foundational stuff to learn first, I think.
Correct.
Right? Okay.
It's very hard to, I've had maybe 2 or 3 surf students over the years where I've been able to give them some well-defined problem that they could understand what the problem was without understanding the real background behind it. But it's very hard. There's too much to know for an undergraduate to do mathematical physics. And that's true throughout the country. I'm not really, there may again be, but you don't major in mathematical physics, you major in mathematics or physics. Mathematics has always had, as far as I know, I haven't kept track since I stopped being since 2014, but it's always had on the order of 20 or 25, between 15 and 25 majors, which if you think about is a very small number overall, but in terms of the size of the faculty, we probably have the largest faculty, smallest, student to faculty ratio, because we're 16 or so faculty, and right there. Well, and computer science is probably also, because it's now there are so many computer science. So I don't think there's been much impact on mathematics in terms of and it's your question in some sense. Undergraduate teaching is both very important and not very important. In terms of Caltech deciding where it puts its resources, it doesn't care what undergraduates major in. It's looking at where the important scientific discoveries are being made. It's only important to the extent that if some area is small and it winds up with a huge number of students, then they can, we have to do something because we can't. And that has happened probably. There's probably been a growth in some of the parts of computer science because they need extra faculty to handle the number of students. But I suspect it's not affected PMA a whit. The size of PMA is the same size in terms of faculty that it's been my entire time here. And the rough ratio of number of astronomers, number of mathematicians is about the same. Our teaching, again, most of our teaching hours are in fact the required core courses, which everyone has to take. That's in one sense shrunk, and in a different sense hasn't shrunk. It's shrunk in the sense that there used to be 2 years required. There's now only 1 year required, but my impression is that the second year, which didn't used to be required of all students, almost all students take anyway. So I don't think there's been a huge in terms of undergraduate teaching impact on mathematics at all, and certainly not mathematical physics.
Barry, to the extent that you could compare, of course, you were an undergraduate at Harvard, graduate student at Princeton, professor at Princeton, professor at Caltech. To the extent that you can compare in these very different aspects or timelines in your career, where do you put the strength of Caltech students relative to these competing institutions?
So there was a period from about 1995 to 2002, I taught Math 1A. So I gave a pep talk on the first day to the students. And one of the things I told them is that, I have bad news for you. Half of this class is going to be in the bottom half of the class. And then I said, and I won't claim that Caltech's top students are better than the top students at Harvard or Princeton or Stanford, but our 50th percentile is quite a bit better, and our 20th percentile is infinitely better. So Caltech's undergraduates, in terms of being fantastic all the way down to very near the bottom, there's no place close in the U.S., not any place close.
What accounts for that? Is it just the selectivity in admissions? Is it the kind of student that wants to be at Caltech?
It's a combination of two facts. It's the kind of students that wants to be at Caltech, and it's the kind of student Caltech wants. So Caltech picks students based almost entirely on whether they're burning to be scientists. Right? Two of my classmates at Caltech in my year, one was governor of Massachusetts, one, well, because of the family it was in, was the publisher of the Washington Post. Caltech doesn't have students like that. Harvard wants to look for students like that. So in terms of when I say comparable, I don't mean in terms of some sense of what they're going to accomplish. I mean in terms of academics. Harvard searches for very different kinds of students from Caltech, and it winds up with very different kinds of students.
And MIT, what about MIT?
So MIT is probably comparable in many ways. I haven't as much experience with MIT.
Of course, it's much larger. It's huge.
And my impression is because it's so much larger, it doesn't quite have as good a student body. But MIT may be the one place that has, that my statement about 20th percentile isn't quite correct.
Barry, between how small Caltech is and because of how idiosyncratically it's organized with the divisional structure. So for you, for professors, what is the most impactful position? Is it division chair? Is it provost? Is it president? Over the course of your years, what, in terms of a new person coming into those roles, has made the most difference to your day-to-day?
Presidents are irrelevant. They raise funds. Well, they're irrelevant except they run the institution. So in that sense, right, I talked about this crisis in 2000. One of the things that we wanted to do was we wanted to hire a fresh PhD as a full professor. It's a long story. It was, in fact, a brilliant choice. We unfortunately eventually lost him to MIT, but he's really good. He made it. And even Michael Aschbacher, who's probably a toughest judge said, well, the only way of thinking about this is this guy wrote such a spectacular undergraduate thesis in Russia. that the only way to think about him is that was his PhD. And so in graduate school, he's been like a postdoc and done some very good things. So it's time to give him that. The one time that the president almost shot us down is David Baltimore decided that it made us look desperate to make this offer. The offer, because it was such an unusual offer, while it sailed through the division at the IACC, it was a 3-3 vote. And officially, it was the provost's decision, because that's how Caltech works. But Baltimore was really pushing hard not to do it. And Tombrello and I who was the division chair, had a critical meeting with Steve Coonan, who was the provost, and convinced the provost. But in terms of day-to-day things, except, of course, the president in the end could have said, yeah, it's officially your choice, but I order you. President does run the institution. Provost officially reports to the president, but basically, president is almost irrelevant for the way provost is very important because he controls all the resources. Division chair is also very important because within the division, he controls the resources. So as an individual professor, probably the division chair is the most important. As an administrator in mathematics, where I have to worry about money for various things, the provost becomes a little more important. So when I was EO in mathematics, the attitude of the provost, not that I ever got to deal with the provost, right? It really is true that the first approximation, the provost deals with the division chair, not with individual faculty, in the level of making decisions on what's going to happen with resources. But of course, that's true at the small scale that someone like me works. It wasn't true, for example, with LIGO, that the attitude of the provost was very important, and individual professors were involved. But
Barry, did you mostly manage to escape from high-level administrative responsibilities?
Of course. So I came in 1981. The EO at the time in mathematics was Wim Luxemburg, who I had thought had the job forever. It must have only been a few years before I came, because Gary Lorden claimed that I served 10 years eventually as EO, and he claimed that it was longer than Luxemburg. But Luxemburg, I thought had been, and I don't know what the details were. It had something to do with he couldn't keep within budget. But at some point, Ed Stone, who was division chair, decided to fire him, called me in and said, I want you to be EO. At the time, I was presumably 42. And I said, I'm too young to die. I won't take the job. And he couldn't believe it. And, eventually in 1998, when I was 50 something, I agreed to take the job. And I had it on and off for, there was a period of 3 years. It's a long story about what happened, but in some sense, I was virtual EO even for the short period I wasn't, because the person who was then EO was not very good, and Tombrello, who was used to dealing with me, dealt with me anyways. But so I was EO for quite a while, but it wasn't so bad. One of the things you have to realize, so I was never more than EO, never a dean, never. And EO is it's not like a department chair. I didn't, for example, as EO, I didn't know what anyone's salary was. I had nothing to do with salaries. I had relatively little to do with recruiting. That's all done by the division chair, not by the EOs. So it's not that onerous a job. And I had the world's best secretary, which helped a lot. And it was still true. I still remember when I was at Princeton, we tried to convince successfully. Some number of us tried to convince the chair, who was very good, to take another term. And I went to see him and I said, he said, the problem is the following. This is only a half-time job. The problem is it's every other 5 minutes. And the issue with EO is that it's not every other 5 minutes. It's every third 5 minutes. It's not, it really is a quarter time. But when something comes up, it really has to be dealt with, not always, but often it needs to be dealt with now. You're writing a paper, well, you postpone it for a week because something comes up. It's not a big deal. There's some crisis that happens and it needs to be dealt with now. But it wasn't so I think I avoided most of it.
Barry, the last topic I'd like to engage with you on for this first session is the way you see connections or lack of connections between your science and your Torah. So at a very basic level, scientifically, you'll notice I did not say spiritually, but scientifically, do you tend to separate out those worlds in terms of your thinking, about your sensibilities, about your intuition? Are they different, yes, or is that impossible?
No, I think they're very different. The Judaism structures how I deal with my everyday life. The science is what I do. It's not, and I try to avoid, unfortunately, with one exception, the famous Torah codes controversy. I try to avoid getting involved in some of the controversies that have occurred in the religious world between science and Torah, because it's basically usually on such a low scientific level.
Right.
And there are, if you look at the deep intellectual Jewish history, there are actually usually pretty good answers to a lot of the issues, but there's no point in arguing with. I'm not someone who likes to get into arguments.
No, I don't mean. I mean at a much more personal level, not in terms of.
No, so politics. I don't.
In other words, I'll give you a very concrete.
I read the Torah portion of the week, and I don't say to myself that couldn't have happened. It's not scientific. It just doesn't. Basically, I'm of the opinion that there are parts of the Torah that are not intended to be taken literally, and so I don't take them literally.
I'll give you a very specific example. So, if you wrestle with the concepts of Echad and Yachid, right? Do you feel like you have a deeper understanding because of your mathematical background? Or in wrestling with Echad and Yachid, does that yield insights into your scholarly world that might not be available to your secular colleagues?
No, I'm schizophrenic. I don't really, no. I've separated. They're not integrated.
I'll flip the question around. As you well know, so many physicists delight in their atheism,
yeah,
because of how they understand how the universe works.
Mm-hmm.
Do you see yourself as a specific counter to that you have insights in both Torah and in math and physics for which it's entirely plausible why the universe has a creator, or even has a creator that's involved in our existence?
So I don't spend a lot of time worrying about this, but I did sometimes in my life I thought about it and I came to a peaceful whatever. But, I remember, one of the people who most delighted in this, because his father was so anti-religious, was Dick Feynman.
Right.
And Dick and I actually had a number of interactions that we can talk about it at some point.
Yeah.
But at tea one day, we were going up to the colloquium. Someone turned the light on and off. So Dick looked at me and said, you know, there are people who say that causes a fire, so you can't do it on Shabbos. You know, there are lots of arguments. I said, Dick.
Did he really say that? Did he really grossly
Yes.
misunderstand Shabbos?
Yes.
Wow.
So I said, Dick, we could argue about this, but we wouldn't agree. So why do it? He looked at me and said, you're right. I wasn't going to argue it.
Operating in a secular environment, do people think that you're a rabbi because you look like one?
Not Caltech, certainly.
Are you regarded as one?
No. You'd have to ask them.
Right.
Right. I don't feel like people treat me any differently from anyone else. Now, that may be because I'm not terribly observant of. Right. I'm interested in my research, and my interactions with people tend to be at a scientific level. And so I'm not tuned in on how they're necessarily thinking about me. But I don't really think I'm treated very differently by my colleagues here. And to the extent that I'm treated differently elsewhere, it's because, you know, I'm the big shot. People want to be nice to me. And so they're worried about kosher food and other such things. But then I have not personally felt this. But you'd have to ask other people if they think of me differently. I know the Chabad rabbi here thinks I'm, you know, this whatever because I'm a symbol of something, and maybe I am to some people, but I don't think of myself that way. The few times there have been students on campus who have a religious interest, there was one period when there were 3 students on campus who had some real interest, and we would have them for Shabbos, 4 students actually. We would have them for many Shabbos. It was a bit of a pain because they had to we're not near campus, and they had to get to us on Friday, which would be a bit of a pain for them. But
because you are undeniably a symbol, I mean, are there other, in the United States at least, are there other eminent kippah-wearing mathematicians or physicists that you know?
Absolutely. So there was a point when Harvard had 3 religious mathematicians on the senior faculty. There are even now 2 kippah-wearing mathematicians on the faculty at the Quran Institute. Both of whom I know. I mean, the ones at Harvard, it's not that I didn't know them, but I didn't know them well. The ones at the Quran Institute, one is my former student who was not religious when he was my student, and the other is someone I've known since we were graduate students together. So.
And in operating in a secular environment, have you ever been challenged? Like, oh, come on, Barry, you don't really believe this stuff.
The only time was this interaction with Dick. Otherwise, nobody. Oh, there was actually a different story. I'd forgotten about this. So there was probably about middle 1990s. You know, Caltech was run by physicists for many, many years. The president was always a physicist. And at some point, the biologists decided they really wanted more respect. And so they arranged a lecture series that was probably early Friday afternoon, because I remember I had to stop going because it was running too late because when Shabbos was coming in. But they had a lecture series, which I think they called Biology 101 or maybe something like that, that you had to be a faculty member to go to these lectures. And most of them were given by Caltech faculty members, but they had one where a guy came from Berkeley. And this was long before the human genome was discovered, was totally understood.